Okay, 8-2 is about special right triangles. Okay, they're special because they're used more than other kinds of right triangles. Okay, the first kind's if you take a square and you cut it in half diagonally, you get a right triangle. Okay, the angles created is 45, 45, and 90, and so it's called a 45, 45, 90 right triangle. Okay, now because it's an isosceles triangle and also because it's half of a square, um, these two legs have the exact same length. So if this one was 5, this one would be 5. Okay? If this one was 7, this would be 7. Say these two legs have the exact same length in a 45, 45, 90 right triangle. So here's a couple of examples. Now I'm going to use the Pythagorean theorem to figure out what the length of the hypotenuses are. But my goal is to find a faster shortcut instead of doing this every time. But this is x, and these are all right triangles, so the Pythagorean theorem works. So 2 squared plus 2 squared is equal to x squared, x being the hypotenuse. So 4 plus 4 is equal to x squared, and x squared is equal to 8, and so x must be equal to the square root of 8. Now making a factor tree, 8 becomes 2 and 4, 2 and 2. I have my pair, a perfect square, so x is equal to 2 root 2. 2 root 2. Okay, let me move this out of my way. Okay, 5 and 5, again I'll call this x. 5 squared plus 5 squared is equal to x squared. 25 plus 25 is equal to x squared. 25 and 25 make 50. So x is equal to the square root of 50. To simplify that, again, I'll make a factor tree. 50, let's say 2 and 25. 25 is 5 times 5. I have a perfect square. So x is equal to 5 root 2. 5 root 2. Now, if we did this last one, we would get 1 root 2. So if you'll notice, there's a pattern of if the leg is 2, the hypotenuse is 2 root 2. If the leg is 5, the hypotenuse is 5 root 2. If the leg is 1, it's 1 root 2. There's a pattern in the textbook. Textbook puts it this way. In a 45, 45, 90 triangle, both legs are congruent, and the length of the hypotenuse is root 2 times the length of the leg. I think this equation is pretty helpful to us. Okay, an example. Since the leg is 7, I just saw the pattern was that this must be 7 root 2. Again, you can use the Pythagorean theorem, but that's what it's going to be. In this one, where the hypotenuse is 8, it's kind of harder to figure out what x must be. I'm going to turn to my formula of hypotenuse is equal to 8, is equal to the square root of 2 times leg. The hypotenuse is 8. Square root of 2 times the leg is x. Let's see here. To get x by itself, I divide both sides by the square root of 2. Okay, so x is equal to 8 over the square root of 2. Now, unfortunately, this isn't in simplest form. So the way I simplify is multiply top and bottom by the square root of 2, which is what the denominator is. And 8 times root 2 is 8 root 2. Divided by root 2 times root 2 is root 4. Now I know that the square root of 4 is equal to 2. And 8 over 2 simplifies to be 4 over 1. So this is equal to 4 root 2. Okay? Now, there is a shortcut to this as well, if you remember it. In a 45, 45, 90 right triangle, you take the hypotenuse and divide it by 2 and get 4, this 4, times the square root of 2. Okay, so if you take half of the hypotenuse and multiply by the square root of 2, that will work. That'll be equal to the legs. Okay, here's a couple of examples. Now, just to check your work, h will be equal to 9 root 2. X will be equal to 4. This x will be equal to 3 root 2. And x is equal to 5 root 2. Moving on. The other kind of special right triangle is half of an equilateral triangle, which if you cut it in half, you get a 30, 60, 90 right triangle. The important thing about the side lengths here is that since we've cut it in half, this leg is half of the hypotenuse. Okay, so here's a couple of examples. If this shortest leg is 4, then the hypotenuse must be 8, since it's double. If the hypotenuse is 12, the shortest leg must be 6. In this, if the shorter leg is 3, the hypotenuse must be 6. Okay, again, this is a right triangle. We can use the Pythagorean theorem. 4 squared plus x squared must be equal to 8 squared. 4 squared, 16, plus x squared is equal to 64. So here, solving for x, I'll subtract 16 from both sides. X squared is equal to 48, and x is equal to the square root of 48. So to simplify this, I'll use a factor tree. Let's see here, 4 times 12, 4 is 2 times 2, and 12 is 3 times 4, and 4 is 2 and 2. So I have a pair and a pair here, which gives me perfect squares. 2 times 2 root 3 is 4 root 3. Sorry, it's all jumbled. Yeah, group some things here. Okay. Now the pattern, if we did the other ones as well the same way, here we get 6 root 3. Here we get 3 root 3. You'll notice there's a pattern of whatever this shortest length is, that times root 3 is what the longer leg is. 6 times root 3 is 6 root 3. 3 times root 3 is 3 root 3. That's the pattern. The textbook puts it this way. Again, I think that these two equations are pretty helpful to us. The hypotenuse is equal to 2 times the shorter leg, and the longer leg is equal to the root 3 times the shorter leg. Okay, a couple of examples. That side doesn't really matter. Okay, that side doesn't really matter. So, let's see here. If the hypotenuse is 12, the shortest side must be half of that, or 6. Okay, and the longer leg is the shorter leg times root 3. So x must be equal to 6 root 3. And I'm done. In this one, the hypotenuse is 6. The shorter leg is, well, half of 6. So x must be 3. Which, by the way, this longer leg would be 3 root 3. All right, a couple more examples. If the hypotenuse is 40, the shorter leg will be half of that. So half of 40 is 20, and the longer leg is the shorter leg times the square root of 3, so it's 20 root 3. Number 2, if the hypotenuse is 10, the shorter leg is half of 10, or 5, and the longer leg is 5 times the square root of 3. Okay, number 3 is a little more interesting. The longer leg is 2 root 3. So y, the shortest length, times the square root of 3 is equal to 2 root 3. So y must be equal to 2. So that 2 times root 3 is 2 root 3. So if the shorter length is 2, the hypotenuse is double that, and x must be equal to 4. Okay, a few more practice problems. We don't have time to do this right now. Okay, one last type of question I want to talk about is the side lengths of a triangle are given. Determine if the triangle is a 45, 45, 90 triangle, a 30, 60 triangle, or neither. This doesn't have any doubling going on, any pairs, and this doesn't look like it's going to be 40 root 3, so this must be neither. Number 8, although I have a double here, just like a 30, 60, 90 triangle, 30, 60, 90 triangles have root 3, not root 2. So this must be neither as well. In number 6, oh, these two are the same, and I have a root 2 pattern going. And so this must be a 45, 45, 90 triangle. Number 10, oh, I have doubling, just like a 30, 60, 90, and I have a root 3. And so this must be a 30, 60, 90 triangle.